talk. The second talk will be given by James Pond of ANSYS on the title Next Generation Photonic Design. James Pond was a co-founder and CTO of Lumerican and was a driving force behind the company's core software algorithms, technology, and advanced photonic modeling capabilities. He has 2 decades of experience in optical and photonic simulation and is the author of numerous papers, patents, and conference presentations. Currently, he is principal product manager at ANSYS, where he continues to work on the core photonic technology, in addition to integrating numerical products into the ANSYS portfolio. Okay, so the floor is yours, James.
Right. Thanks very much for the introduction, and thanks for inviting me to give this presentation. I just want to check you can see my slides correctly.
Yes.
Great. Yeah, so I'm here to talk about next generation photonic design. And what I'm going to do is give a quick introduction and motivation, and then work through some interesting examples of photonic inverse design, a few more details on optical transceiver design, then some coupling of with ray tracing and augmented reality, heads-up display and OLED displays, and then talk a little bit about some longer-term work we're doing in quantum photonics. Just in terms of motivation, I think over the last 30 years, the progression in photonics has been just absolutely incredible. And now we see photonics all around us, in our homes, in our consumer electronics, pretty much every device we have. We also see it a lot in industry, a lot of sensing, industrial IoT, and so on. A lot of infrastructure and security. It has a big role to play in the 5G rollout and things like LiDAR systems for autonomous vehicle navigation. We see it in sensing, in healthcare, medical imaging. We also see it in things like rapid DNA sequencing and things like that. And of course, photonics has a huge role to play in the data centers, which are a very important part of our infrastructure today. They're responsible for a lot of the optical transceivers for high-speed data communications, but also there's sort of evolving use of photonics in AI, machine learning applications, as well as in the future in quantum computing and quantum information technologies. In terms of photonics, I think everybody here is probably pretty familiar with what it is. I'll just say in terms of how we speak of it, we tend to find amongst our customers that there's a bit of a split between those who are doing integrated photonics, which you see on the left here, which is really, it looks a lot like integrated electronics. It's things that are made in high volume, low cost manufacturing at foundries like Global Foundries or Tower Jazz. There can be silicon photonics as well as other material systems like indium phosphide and silicon nitride. And then on the right-hand side, we have what I roughly call nanophotonics, so sort of wavelength scale photonics, looking at things like scattering from rough surfaces, plasmonics, where we have, resonant type structures, like you see here. This might be used for fluorescence enhancement or even looking at defect scattering on surfaces. And then in the middle, we have a kind of a gray zone, things like OLED displays, micro LED displays, CMOS image sensors, which are manufactured in a lot of the same foundries as integrated photonics, but they're sort of a little bit fundamentally different in terms of the geometry and the types of things they're doing. So we tend to group this display and image sensor along with the other nanophotonics type of devices. So I'm going to talk about some applications when we get to it in both of these areas. Now, in terms of, I just want to give some examples of the complexity of problems that our customers are trying to solve. One of them is to try to make very high speed optical transceivers for data centers and other applications like in co-packaged optics. And the basic idea that people are trying to solve is to take digital signals, which very, very high-speed digital signals going into an electrical driver. That electrical driver is then going to control modulators, which may be modulating individual wavelengths of light in different channels, which can get multiplexed, taken through a fiber coupler out to an optical fiber, maybe propagate some meters to 100 meters, or even further, where they're brought back onto a chip in a fiber coupler, demultiplexed into the different wavelengths, brought into high-speed photodetectors, turned into a photocurrent, which goes back into an electrical receiver, obviously a complex and high-speed circuit, where it can be converted back into a digital signal. So you can get these digital signals from point A to point B. And, you know, obviously, people are always trying to improve the performance, reduce the amount of energy consumed, and get things going faster. And you can get it going faster by doing things like increasing the symbol or baud rate. You know, you can go from 10 gigabaud per second to 25 and increase the speed. You can also increase the channel count. So what I've shown here is 4 channels, but you could have, you could increase that to 8 or 16. And you can also start to try and pack more symbols per channel. So, you know, we often think of a 0 and a 1, but you can have a 4-level signal like PAM4, or you can do more advanced things with polarization and phase to start sending many, many signals in each channel. Now, you know, we have customers optimizing a lot of these individual components in a system like this. We also have customers who want to simulate the whole sort of photonic link, which is something that we do. And then we have customers who want to, you know, try and simulate the entire system, including the electrical drivers and receivers. And there we partner with other electronic design automation companies and do something we call electronic photonic design automation to try and solve this problem. Now, another example I want to give as motivation is, you know, people who are trying to design camera systems for autonomous driving. And this is a really complex problem. So, you know, there are various aspects of it. You've got the subsystem camera design, you've got lenses to design, you've got image sensors to design, you've got electrical charge transport to deal with. You also have, you know, what is the environment that you're going to be driving in? Is there going to be fog? Is there going to be, is it daylight or nighttime? And how's the system going to perform under those conditions? And then you've got, you know, the systems that actually process the images, the image processing software. And you want to be able to see, kind of considering all of this, you know, is your entire system going to perform? And you want to be able to optimize it. And you might even want to optimize it in these very complex dynamic driving scenarios, say, where you can see, you know, will I be able to recognize the things I need to recognize, and will I be able to do that in different lighting conditions? So when you look at those two examples, it shows a whole range of different challenges that we have when it comes to simulation. First of all, the problems are highly multiphysics. There's optical, thermal, electrical, mechanical, and even quantum effects. If you're looking at, say, the lasers that are required for something like a LiDAR system or a communication system. The optical challenges alone, the devices have to operate at multiple wavelengths. The materials are complex, metals, semiconductors, organics. And then you have things like liquid crystals or potentially magneto-optical effects, or 2D materials like graphene, maybe nonlinear effects. On the electrical simulation side, you know, there's charge transport, but often that has to be coupled with multi-quantum wells. You may have 2D charge transport in materials like graphene. You have coupled electrothermal issues with self-heating. There's also a huge range of geometric scales, like my colleague in the previous talk talked about as well. And you have this whole issue of device level to system level. You know, at some stage you want to be optimizing like individual components, and at other stages you want to be going and simulating the entire system to see how everything works together. So now I'm going to just show some examples of how we're trying to address some of these challenges, and focus, you know, on some of them. I think some of the most interesting recent work that we've been doing. So the first thing I want to talk about is photonic inverse design. So the idea of photonic inverse design is that instead of focusing on, you know, the actual design itself and figuring out how it performs, we focus on defining the figure of merit that we want to achieve. And then once we have that figure of merit, we want to go into an iterative loop where we actually, you know, try to create a design that achieves the performance or functionality that you're looking for. And something we've done in recent years is work a lot with the adjoint method. in order to do this. And the reason why is that the adjoint method can give you the gradients, not just the figure of merit, but the gradients of the figure of merit very, very efficiently. In fact, the way the adjoint method works is that you essentially have to run two simulations. You run a forward simulation, which is basically where you inject the light that you actually, basically in the setup that you would normally run just to evaluate the figure of merit. And then there's an adjoint simulation where essentially you're injecting in reverse what you want to get out of the system. And by combining these two simulations, we can actually extract not just the figure of merit, but its gradient to any number of parameters. So even if you have 100 parameters, you can extract out all of the gradients to all of those parameters from just two simulations, which seems amazing, but that's sort of the beauty of the adjoint method. I don't have time here to get into all of the details, but I'll say that the work we've done started as a collaboration with Christopher Corrali, who did his PhD with Eli Yablonovich at Berkeley. And that morphed into an open source project called LumOpt. And it drives our software using our Python API, and therefore, we've been able to create this great workflow for this type of optimization. And I put a couple of references in here as well on generally using photonic adjoint methods in photonics that may be relevant if people want to dig into the details a bit more. So in terms of the adjoint method, there are two flavors of it that are quite interesting. There's shape-based and topology-based. A shape-based is more what you would naturally think of for optimization, where you define a number of parameters, like in this case, control points for the edge of a waveguide. And topology optimization is much more free form, where you just say, okay, here's a block of material like silicon, and create what you're going to create to give me the figure of merit that you want, and every single position of space can be modified. So we'll start with shape-based. So we've done a fair bit of work on this in terms of, say, starting with simple examples like defining a really high performance Y splitter. So this device was actually done in a co-optimization effort where we optimized two figures of merit, one where the device is over-etched and one where it's under-etched compared to the nominal. And we sum those two figures of merit. And as we go through the process, we've got this device parameterized with a cubic spline along the edge of one wall. And so you can see that it goes through several generations. Each generation takes 4 FDTD simulations to apply the adjoint method for the two figures of merit. And we end up with a nice design. And this was actually done as part of a workshop. And so you could actually get through this design in 20 minutes, 30 minutes with a laptop. And at the end of it, we'd get a layout where you can use cutback measurements to measure the performance of this device. And because we did this workshop with collaborators at University of British Columbia who actually could manufacture them, the students could get them manufactured right away after the workshop and get some results. And this device that you see here is actually one of the best performing Y splitters in the world. And using this type of approach, you can design it in 20 or 30 minutes on a laptop. And this device is not only high performance, but it's very robust if the device becomes a little bit wider, a little bit narrower in the manufacturing process. So now moving on to topology optimization, this is where you start to see something like this kind of appear. So here you just give sort of this free form bit of silicon and you try to define, try to create something similar, and you end up with these patterns that look a bit like Swiss cheese. Now for the Y splitter, it's maybe not so interesting because we have a very good design anyway with using the shape-based methods. But so we started trying some more exciting problems here. And one is to make, say, a 4-channel wavelength demultiplexer. And the idea being that we would give only a 6x6 micron region of silicon and try to split 4 channels out in the O band. This device would be 36 microns squared, which is orders of magnitude smaller than conventional devices to achieve the same performance. So this is what it looks like when you run it in a topology optimization method. And you can see that it goes through a few stages, kind of a grayscale phase. And then one of the things we had to introduce was a minimum feature size constraint, so you can actually build it. And you see that kind of kick in at the end, where everything suddenly becomes a lot less small, let's say, and a lot closer to something you could imagine being manufactured by photolithography. The performance of this device is really good. So pretty exciting. And if you see the field profiles, it's really quite remarkable to see what can be achieved through this type of optimization. Now, before we get too excited about this, I want to say this is a first trial with a two-dimensional problem. So this is a two-dimensional optimization. So it's not something that will actually work in 3D. And we have been working on this device in 3D and making some progress. But one of the earlier devices we tried in 3D is a little bit simpler, which is just a OC band splitter, where you can separate those two telecommunication bands. And we came out with a device like this one. And you can see we have it manufactured. We have an SEM. We know it matches what we wanted. And we know from simulation that this device is going to work, and we're just waiting on some of the measurements for this device. But I have no doubt this will work because this is the FDTD simulation, and as I say, we know the device was manufactured as expected. So we're eager to see some of those results. So now I want to talk a little bit about optical transceivers. I think as people here are probably aware, the key part of the optical transceiver is the modulator, and that's normally done with a Mach-Zehnder interferometer, where you separate the light into two arms, and then you adjust the phase on one arm till you find a certain operating point, and then you send in you have an electrically controlled phase shifter, where you apply a certain voltage signal, which brings you between 2 points, either constructive or destructive interference, which are essentially your zeros and ones in an on-off keying setup. If you do something with, say, PAM4, then you can have two phase shifters for a least significant bit and a most significant bit. And in this case, you can actually sort of send in various combinations of zeros and ones to get you to the 4 different levels, which allows you to send 4 symbols instead of just 2. And basically double the communication speed that way. Now, if you're trying to use this in an actual system, here's a schematic diagram of the system. It has electrical parts and it has optical parts. And I'm not going to get into all of the details, but when you have these two phase shifters, you need to make sure that the electrical signals arrive at very precise times on each of the phase shifters. Basically, it has to account for the delay for the light to get from phase shifter 1 to phase shifter 2. And so it becomes a very complex system level problem to simulate and optimize. So how we can do that, on the left here, we can draw a schematic in our interconnect product, and we have behavioral models for each of the different elements here. And we have not only sort of ideal behavioral models, but also statistically enabled behavioral models. So we can run Monte Carlo analysis of this type of device, and we can look at, say, how the different levels of the PAM4 will vary as we run into manufacturing problems. And in addition, we work with our EPDA partners like Cadence and Mentor Graphics to be able to do the more system level type of simulation. And in particular here with Cadence, what's really interesting is that we're doing a simulation, a co-simulation of the electrical drivers and the entire photonic link. And what you're seeing happen in the 4-level eye up here is seeing what happens as we go in and out of optimal timing of those different electrical signals. So as they get out of time, we find that the eye gets distorted and our signal integrity is reduced. Okay, so I now want to talk quickly about augmented reality heads-up displays and displays. And this is creating the link basically between the wavelength scale optics that the numerical team at ANSYS was known for, with some ray tracing capabilities that ANSYS has with a product called SPIOS. And so we can extract surface properties from different wavelength scale devices meta lenses, that type of thing, and bring them into SPIOS to do ray tracing. And I just want to touch on a few of the things that we can do here, from everything from sort of CMOS image sensors, stray light analysis, to diffractive optical elements, and surface scattering, and so on. A specific example is the automotive heads-up display. And so the idea here is the question we were looking at is whether we can use plasmonic devices to actually create a better contrast heads-up display that's polarization sensitive. And so the idea is you put these very small plasmonic particles on your display, and you have on your windscreen of your automobile, you have a display underneath which has naturally polarized light, just the way the display is designed. And you want to make the best possible heads-up display. So we ran some optimization targeting certain reflections for different polarizations. And you can see some movies here of the FDTD simulations running for the two different polarizations of incident light. And it's not so obvious in those movies, but if you look at the reflection, transmission, and loss spectra across the visible, they're very different for the two polarizations. And we sort of target a perfect amount of reflection at the 30 degrees incidence, which is kind of how the geometry is set up. And in the upper right here, you can see that we can achieve a really beautiful contrast heads-up display with this plasmonic surface, where we're basically targeting both the spectral reflections as well as the polarization of the reflection to kind of have an optimal setup with the display that we have. And another area we've been working on is OLED display. So we can calculate the emission both as a function of angle and wavelength for these types of OLED displays with red, green, and blue pixels, as you see on the right here. And then we can bring that information into SPIOS. So what we calculate with our stack solver, which takes into account all the coherent effects in that multi-layer OLED display, is the power density as a function of angle and wavelength for each of the structures. And then we have to overlap that power density with the actual emission spectrum of the red, green, and blue displays. And when we do that, we can get out the actual spectrum for all wavelengths and angles, and we can load that up into the ray tracing software. And that allows us to look at, what is say a cell phone that uses this actual display going to look like. And here's where you can really see some of the interesting effects. For example, here you see a really poor color shift where the display goes very greenish when you look at it at an angle. And this is because this display was really optimized for efficiency, power efficiency, but not necessarily for color at angles. And we can even look at things with the SPIOS software, like the human perception in different lighting, so nighttime versus daytime, as well as looking at legibility for different ages of people, someone who's 20 years old versus someone who's 60 years old, say, and understanding under what conditions they'll actually be able to read this display. So it gives really amazing opportunities to optimize displays for a variety of applications. And now, just before getting to the end here, I want to talk a little bit about quantum photonics and some longer term work we're doing. Today, we have quite a number of customers who are doing quantum photonics or quantum information technologies with our software, but the main thing they're doing is actually optimizing the individual components that go into their quantum systems. So they're basically doing classical simulation to try and achieve certain specifications for different components. And that's the kind of thing that was done here on the left, say, for this single photon detector. And on the right, there's some examples of sort of very high quality factory devices that are used for some quantum applications. But what we want to do is try to go a little bit beyond this. And so just to give some background in quantum photonics, you can actually create qubits using linear optics and waveguides. And the idea is if you have two waveguides A and B, you can characterize this with a Fock state where you say have one photon in waveguide A and 0 photons in waveguide B, and that would be your logical qubit 1. And then you can have the opposite. We have one photon in waveguide B and none in waveguide A, and that would be your logical qubit 0. And you can very quickly see that if you create a directional coupler and you send in one photon into waveguide A, and then you have some directional coupler that mixes, has some output to waveguide A prime and some to waveguide B prime, that you're going to end up with a state that's actually, the photon is living partly in each waveguide, and this is going to be a superposition of your logical 1 and your 0. So this is a fairly simple way of looking at it, and I would say that as soon as you get more than one photon, this gets very, very, very complicated, and your Hilbert space gets big very fast. But this is the type of problem that we've been looking at recently. And if you look at, say, how we would use our circuit simulator to do classical analysis, this is often by calculating the S matrix of a given circuit. And there's a link between the classical S matrix that relates the input and output of classical signals and the quantum S matrix that relates the input state, the quantum input state, to the quantum output state of the same circuit. The quantum S matrix is a nonlinear version of S, and it's much, much bigger as soon as you get above one photon. And in addition to that, we can define measurement masks, which reduce you to a subspace that corresponds to a particular measurement that's being achieved. So unfortunately, I don't have the time to get into all of the details here, but the really exciting thing that this allows us to do is to be able to look at things like an interferometer like this one, and this is used for boson sampling applications. And what we can do is look at not just the performance from the ideal device, but because we have all the capability I mentioned earlier to do Monte Carlo analysis with statistically enabled compact models, we can actually look at what happens when there are real manufacturing errors in this device. And so what you see here is a diagram showing the effect of splitting ratio errors in all of these directional couplers, and the statistics of what that's going to do to our output measurement in this boson sampling case. So I know I'm at the end here, so I just want to conclude by saying that photonic design now has many challenges, very multi-physics, very device to system level, many length scales, optical, electrical, and other challenging simulations. I think ANSYS is really ideally positioned to solve a lot of these problems. We have not just the photonics capabilities in optical, but actually a whole host of other physics-based simulation capabilities that allow us to solve and address a lot of these very complex problems. So thanks very much for your time.
Thank you very much for your very interesting talk. So we have a couple of questions. If you have more questions, please write in the Q&A tab. First question is from EC. How do you know if the reverse designed feature is manufacturable?
Yeah, that's a great question. It's a challenge for sure, especially if you're looking at that topology optimization. And when we first started doing it, we were very quickly creating devices that are not manufacturable. I would say that the standard approach to topology optimization, there is a spatial filter which avoids pixelation and impossibly small features, but nonetheless, you still end up with things that may not be manufacturable. So that's where we introduce this minimum feature size constraint. And that's something that the user controls. So you can say, okay, I know my process cannot make a feature below 150 nanometers. You can introduce that, and it will make sure that there are no features below 150 nanometers. So that's how we know it's manufacturable. The challenge is then that, as you increase that minimum feature size, the performance of your device goes down. So you have to find that balance between what you can build and what actually achieves the performance that you want.
Thank you very much. The second question is from Mark. For the topology optimized 3D channel splitter, how sensitive is device performance to the dimensional tolerance of the structural elements?
Yeah, so that's also a really good question. So that I went pretty quickly, but the Y splitter that I was showing, which is the shape-based optimization, it was deliberately designed to be insensitive to manufacturing imperfections. Because we co-optimized something that was a little bit over-etched and something that was under-etched. And there are actually similar approaches that you can take in the topology-based optimization in order to in order to make sure that you've got something that's robust against manufacturing imperfections and isn't just sort of a hero device that, you know, works perfectly, but you can never really build something close enough to make it work.
Thank you very much. The third question is from Orad. Is your entire topology optimization toolkit only 2D for now?
No, it is 3D. And the example I showed of the O-C-band splitter there was a 3D optimization. Of course, the challenge with 3D is that you have to run hundreds to sometimes thousands of simulations. So if you're going to larger and larger devices, like say grating couplers, which we looked at, I mean, then each simulation starts to take, you know, a certain amount of time. So you have to be a little bit cautious there in terms of the size of device. And it really depends on how many computing resources and HPC you want to throw at the problem.
Okay, thank you. And last question is from Sherry. Can you talk a bit about your abilities to handle widely varying time scales in your circuit simulator?
Yeah, that's a great question. The timescale issue is often big, not just in the circuit simulator. You know, when you're doing these kind of multiphysics problems, in the circuit simulator, it's for the optical part, it's actually an envelope approximation. So we're not solving. So we're not, say, solving the optical field at 193 terahertz for, say, C-band. We're actually solving the carrier of the optical field at 193 terahertz. So that brings the time scale of variation of the envelope into the same kind of range as the electrical signals that are driving the problem. But where you run into the big time scale issues is, say, things with thermal tuning. So if you have a thermal heater that you want to simulate that has a much slower response time, you know, then sometimes we go into more of the iterative type of approaches, you know, where you might assume that, you know, for the optical timescale and electrical timescale, the heater is at a constant temperature, and then take a much bigger time step in a kind of an iterative approach. So it really depends on the problem, I would say, that that we're thinking. Yeah, it looks like you're thinking optical and thermal. Again, yeah, typically we take kind of an iterative approach. One area that's quite interesting is some of the work we've done recently on laser simulation. We have a 1D traveling wave laser model with self-consistent heating now in interconnect, and there we have to deal with the multi-time scale type of challenge in that model.
Okay, thank you very much for your very interesting talk. Okay, so thank you very much.